Welcome back to Koala Nation and the deep dive series of AnimateDiff. After the basics, shown in the first video, we will now delve into more advanced topics. Today we will cover prompt traveling and the use of ControlNet and IP Adapter with AnimateDiff. In addition, we will look into detail how to use context and view options. This will allow us to overcome the limitations of number of frames of the native motion models. This way, we can make animations as long as we want. In the GitHub page of AnimateDiff Evolved you have workflow examples to start with AnimateDiff. However, at the moment of this recording, the template for prompt traveling does not work if you try to use it. Nevertheless, in GitHub we can still have access to the previous commits which still contain the right file. You can go to the before refactor 2 commit and use the prompt travel template from there. Or you can check in my civit.ai article about AnimateDiff and download it from there. I will leave both links in the description. We are going to use the custom nodes recommended in the AnimateDiff Evolved GitHub. For this tutorial, I recommend you to install also the CrysTools custom node, which will be used for some quality of life improvements. When ready, restart ComfyUI and refresh the browser. This version of the workflow still has the old nodes, so the first thing to do is to replace the old node with the 3 generation 2 nodes of AnimateDiff. Add the use evolve sampling node and connect it to the model checkpoint and the case sampler. Connect it also to apply AnimateDiff model node, which then is connected to an AnimateDiff model loader. Change the model to the version 1.4, which we will use in this tutorial. When ready, delete the old legacy node. The text of the batch prompt schedule is a little bit unclear. What I like to do is to use a multiline text box. Copy all the text and paste it into the multiline primitive node. Convert the text widget to input, and connect the multiline box to this new input. Start with changing the prompt schedule text. For the frame 0, use one girl, solo, short hair, red jacket, smiling, city, close shot. For the traveling, use the same prompt but change the red jacket for yellow shirt. Use frame 12. If you want to use more traveling frames, pay attention to the syntax of the prompt. Write first the frame number, between quotation marks, then a colon, and then the prompt, which is also between quotation marks. Check also that there is a comma that separates each of the prompts. Clean it up. You do not need the last comma. Delete the 0 in the app box. We will use in this tutorial the coloring anime checkpoint. Link in the description. Change the scheduler to DDIM uniform. Change the sect in the primitive to 1111 and test the workflow. You can see that the shirt of the girl changes from red to yellow. You can also use different prompts and keyframes to make different variations. Prompt traveling helps on guiding the animation, but with ControlNet we can use the videos or images to further control what we want to do. Add a load video upload node. We will use this video of a flight attendant. Select to take every second frame. Convert the frame load cap into an input. Add a primitive integer. This defines the number of frames to render. Connect it to the video node and set it at 16 for the moment. Convert the batch size of the empty latent to input and connect it to the integer node. For this example, add the HED soft edge and the DW pose estimator preprocessors. Connect them to the load video node and run a preview to check they work. We will use set and get nodes to make the workflow tidy. We create 2 for the preprocessed images which we use later in the ControlNet. You can add now the ControlNet apply nodes. Please make sure you use the advanced ControlNet, because you will need them when processing more than one context window. This is, when making animations of more than 16 frames with this AnimateDiff model. As usual, connect the prompts and the conditionings consecutively and the final positive and negative to the K-sampler. Connect now the ControlNet models to the Apply ControlNet nodes. For the first one, we will use the Soft Edge ControlNet. For the second, we will use OpenPose. Next, connect the ControlNet Apply nodes to the corresponding preprocessed images. The Soft Edge images to the first, and the DW Pose to the second. We will reduce a little bit the weights to give some freedom to the AnimateDiff motion module. When ready, run the workflow. You see now that with Soft Edge ControlNet we define the contour and some of the details, like the scarf. With DW Pose, the pose of the woman is the same as our original video. For animations with people, my personal favorites are Depth and DW Pose or Open Pose. I also use frequently ControlGIF, as it provides additional consistency. However, the choice you make depends on what you want to do. Different ControlNets will provide different results. No good and bad, you need to decide based on experimentation. Like in image generation, we can also use the original images and use less denoise in the K-sampler. In this way, the final video will resemble our original video but with a small twist. Connect the video frames to a VAE encode node. Connect also the VAE and this to the K-sampler. Even with a high denoise, the video is similar to the original. Reduce now the denoise to 0.5 and see what happens to the animation. With half denoise, we only erase half of the information of the original latent, so the final animation looks like the original video but with some style filter applied. Lowering denoise helps in consistency, but sticks too much to the original images. With Image Prompt Adapter, we can adjust the style of the video to what we want with a reference image. It is a very powerful tool to create totally new-looking animations in combination with ControlNet. To start testing IP Adapter, let's do first some changes. Choose the starting frame to be 72. Reconnect the empty latent to the K-sampler and set back denoise to 1. We will use depth anything for the first ControlNet, instead of the soft edge lines. Thus, change the preprocessor and change the ControlNet model to use. Increase the number of frames to 32 to make a more interesting animation. If you try to run now the workflow, an error will appear. This is because the AnimateDiff model we use has a maximum of 24 frames, but we asked to render 32. We can overcome this by using context options in the Evolved sampling node. We will discuss context options as detail later. For the moment, add the standard static options with a context length of 16 and an overlap of 4. Use a load image node. Add your desired reference image. I will leave a link to what I use in the description. Add the IP Adapter node. Use the Prep Image for Clip Vision node to size the image correctly, and then connect it to the IP Adapter. Use Pad as a crop method. Connect now the IP Adapter Unified Loader. Choose VITG as a model, and change the strength to 0.6. Make sure the IP Adapter model is installed. If not, you can do it via the manager. Search for the IPA model, install it and click on Refresh. Connect the checkpoint model to the unified loader, and the model output to the IP Adapter. Finally, connect it to the Evolved sampling node. The result of IP Adapter is an animation with the style of the reference image. This is a short example of how to use ControlNet and IP Adapter, and the result is still not 100% consistent. However, explaining how to do it goes beyond the aim of this tutorial. We may want to do it in future videos. However, you can check my other videos to have a good starting point. Context and view options are next. I reorganize first the workflow and add 2 additional samplers, so we can compare the effect of using different nodes and varying some of the different settings. A template to use to make these comparisons is available in the My AnimateDiff guide page in civit.ai. Context and view options are nodes used to extend the animations and work around the frame limitations of the AnimateDiff models. Context and view options divide the latents in portions defined by their length, with some overlap. Context and view work differently, but we will see it better with the examples. As a reference, we will use standard static. Use the default settings of context length 16 and overlap of 4 frames. It is the same already used in the IP adapter example and works well in most of the cases. In the GitHub example, you see that the frames are diffused in context windows of 16 frames. The context windows move along with an overlap of 4 until all the frames are sampled. This is repeated for all steps, always starting at the first frame. Every motion model has its optimal length to create the animation. With the overlap, we try to increase the coherence between context windows. The higher the overlap, the smoother it is. However, increasing the overlap increases the number of context windows, which increases the render time. Let's see some examples. To visualize better the differences in context length, we will bypass the IP adapter nodes, change the prompt, and change the ControlNets. First, deactivate or bypass the IP adapter nodes. Reconnect the checkpoint model output to the set node, otherwise it will give an error. Change the prompt traveling text. Start the second prompt at frame 16. Add blonde before short hair for both prompts. In the second prompt, change city for forest. Set the strength of the depth ControlNet to 0.3 and the n% to 1. In the reference animation, we will keep a context length of 16 and an overlap of 4. In the second, we will change the context length to 8 and keep 4 as overlap. And in the third, we will only change the overlap to 0. Run the workflow. In the animation in the middle, with a context length of 8, there are more frequent changes in the animation. That is because the number of latents have been divided every 8 frames, instead of 16, so more animations are being made by the motion module. The animations from the left and the right seem more coherent with less changes. However, on the one of the right you can see that at the middle of the animation, there is a more sudden change than in the animation of the right. This happens because on the right we indicated that there was a 0 overlap. So during the rendering, the sampler did not try to blend any of the frames. The option we can select in context options is the fuse method. This sets the method used to weigh the latents during the overlap. There are 3 methods: pyramid, relative, and flat. Again, let's see some examples. For the reference video, increase the overlap to 8 frames. In the second, restore the context length to 16, change the overlap to 8, and choose the relative fuse method. In the third, overlap is 8, and the fuse method is flat. The difference between the animations is subtle. You can really only see the difference if you look at the overlap frame by frame. In the first 7 frames, you can observe the 3 animations are not exactly the same, but they are pretty similar. However, in frame 8 and 9 you can see in the third animation, with flat fuse method, the change starts becoming more clear. The difference between the pyramid and the relative method is minimal. However, in frame 16 we can appreciate that the collar is transforming differently in both animations. In the rest of the animation the frames of all 3 are rather similar. The fuse method affects mainly the overlap. In most cases differences are hard to see. The type of AnimateDiff model also matters. In this other test without ControlNet, the transition between context windows is more different. For flat fuse the differences are higher, but in relative there are some frames that do not look totally nice. In general, the pyramid method seems to provide a smoother transition, but, as usual, experiment with different fuse methods to see what result is best for you. Standard uniform is different than standard static. The first context window starts at a different frame in each step. In the first step, the first context window starts in the first frame and moves along. However, in the second step the first context window starts in the middle frame. This divides the number of the frames in two parts. Then, the context windows try to cover all frames first of the second part, then of the first part. Because of the settings of length and overlap, we need in this step 6 context windows instead of the 5 we had in step 1. For the third step, the division of the frames starts in frame 16. In step 4, frame 48, etc. Following this algorithm, we are trying to spread out the diffusion in different steps, with the intention to increase the consistency of the animation. And the algorithm can become even more complicated. We can also use the stride setting. With a value of 2, every 2 steps there are 3 additional context windows where the sampling skips every second frame. By skipping 1 frame, this algorithm tries to further increase the coherence of the animation. A very complex method is used, but what will really happen? Let's come back to the workflow. Increase the number of frames to 64. We will use only 1 prompt. Delete red jacket and use a forest as a background. Add also behind a tree. We will not use any ControlNet, so you can bypass the preprocessors. Connect the prompts directly to the conditioning get nodes, which will be used in the case samplers. You can also bypass the ControlNet nodes. We are going to use AnimateLCM. For that, add a LoRa loader model only node. Select the LCM LoRa, and connect the node from the checkpoint loader to the get node, which connect directly to the AnimateDiff apply node. We will bypass IP adapter, as we want to get the animation more loose. In the AnimateDiff loader, we are going to choose the AnimateLCM motion module model. To run AnimateLCM, we need to change some settings in the case samplers. So for each of them, set 6 steps, a CFG of 1.5 and choose LCM as sampler. We will keep our first context windows option node with static uniform and the standard settings. In the second, we will change it for standard uniform, with standard settings. See that stride is 1. In the thirds, we will also use the standard uniform, but we will increase the stride to 2. In the first 2 animations we observe very little difference, but we can see that the third one, with a context stride of 2, the animation tries to connect earlier with further context windows. With context uniform and stride, the goal is to homogenize a little bit more the animation, overall, not only within context windows. However, we also see that the definition is not as good as the first 2. When using ControlNet and IP adapters, like in this test, high context stride may create some flickering. However, we can create more fluid animations and reduce the flickering if we concatenate context options. Doing this is similar to what we explained in the first tutorial with scale and effect multival. In this case, connect the standard uniform, with a stride of 2, to a standard static node, and this to the evolved sampling node. In standard static, we define a starting percent of 0.15, so at the beginning, which is more important, sampling is done with the stride. We will set the stride to 2 in the second animation to compare. With this configuration, we obtain the better fluidity of using stride 2, but with minimum flickering or blurriness. As you see, the motion of the third animation is the same as the second, with context stride of 2. However, the images are better defined, to the same quality as in the first animation. For very high precision, specific models or desired effects, you may want to test different strides. However, in most cases you do not want to overcomplicate the things. Standard static or standard uniform with stride 1 are generally good. Fine-tuning of ControlNets, IP adapters and the overlap is more important. The next type of context options is looped uniform. The sampling process algorithm is similar to the standard uniform, with the difference that the animation will loop. This is, it will try to connect the beginning of the animation with the end. Let's run an example. Replace now the standard uniform nodes from the second and third animations for a looped uniform context options node. In the second animation we will use a context stride of 1, while in the third animation a stride of 2. You can see that, when the animation loops, the first animation has a clear cut, while the second and third have a smoother transition. For this reason, the second part of the animations are rather different when you use the looping node. With a higher stride, the animation tries to anticipate the loop earlier, resulting in more differentiation to the static uniform animation. We can also choose if we want an open or closed loop. In this animation we use ball bouncing using a segmentation ControlNet. You can see that the moon follows the pink movement in all cases. However, with standard static, the lines of the horizon change their slope. With looping uniform, the transition is smooth. The difference between closed and open loops is very subtle. The animation in the middle, with the closed looped option activated, blends the first and last frame. For this reason, it positions the moon higher than the position of the pink ball. This way, the loop effect is better. The third animation, with an open loop, struggles creating this first frame, as two moons appear. When using ControlNets that do not loop, like in the video of the flight attendant, the looping will not work. There will still be a difference, like shown here, but most of the benefit of the looped uniform context options nodes is obtained if you want to do looped animations. Finally, we have the view options. This works slightly different than context options. In context options, the latents are portioned, and then each portion is diffused, including ControlNets, IP adapters, motion modules, etc. With view options, the latents are not portioned for parts of the UNet like the ControlNet and IP adapter. It is only divided for the motion module of AnimateDiff. In theory, this method provides more stability to the diffusion, at the expense of using more VRAM, especially with long animations. This method can be combined also with context options, so the view options are only applied to a specific context window. Increase the number of frames to 128. For this test, use only one prompt, adding behind a tree in the prompt. Make sure ControlNets are not active. In the second animation, replace the standard static node for view options only. Connect it to standard static options for view options. Leave the settings to 16 length. Overlap is 4 frames. View options can be combined with context options. In these situations, the sliding window of the view options apply to the context window. At the same time, context window slides over the complete animation following its corresponding sequence. All animations look very similar, but in the second animation you can see, for example, a difference in the color. The first and third are the same, because the context window and the view windows are the same. To combine context and view options, the windows need to be different. Let's modify the second animation and replace view options only for a context options standard static node. Define the context window to be of 128. 128 is the total number of frames, so we need to activate use on equal length, otherwise we will have an error when sampling the animation. We can also concatenate context options when using view options. Insert a looped uniform context options node between the existing one and the evolved sampling node. Set the length to 128 frames and the start percent to 0.16. Set the length of the static uniform node to 32 and the overlap to 16. Replace the standard static view options for standard uniform and set a stride of 2. To the looped uniform node, add view option standard static length 16 and overlap of 4. In the second animation, we have run the view options of length 16 over a context window of 128 frames. This is the same than using view only. However, in the third we do the same but with additional context options that only apply in the first steps. View options allows us an additional degree of flexibility. Its combination may provide additional stability for long animations. For video to video, we may prefer to be simpler and focus in ControlNet and IP Adapter. Today we have seen how to use AnimateDiff with prompt traveling, ControlNet, and IP Adapter. We have also seen in very detail how to use context and view options. In next videos, we will show more advanced features like sample settings, options for the models and other tricks to module and improve animations. I hope that you have liked it. Thanks for watching.